Hi, I'm David, a PhD student at Berkeley, and today I'd like to introduce a way to turn any distributed protocol into one that scales. This is based off of work that we published this year at SIGMOD, which we later extended to BFT protocols at PaPoC, which is a workshop of Eurosys. So let's start by talking about distributed protocols. If you've ever had to write a program that runs on multiple computers or in the cloud, then you've probably had to think about something like voting, 2PC, Paxos, or even BFT protocols like PBFT. Now, you don't have to understand what any of these protocols do or how they work. In fact, the whole pitch of this talk will be that we can optimize these protocols without understanding how they work. Instead, all you need to know is that these protocols may appear simple, but they actually contain a lot of hidden complexities. And these complexities crop up when you try to modify these protocols or prove something about them. Right? But people do want to modify these protocols because they're often the bottlenecks of, or throughput or latency bottlenecks of whatever system they're a part of. So how do people currently go about this? Well, they usually come up with some clever insights and then create entirely new distributed protocols and then prove that these new protocols satisfy the same invariance as the original. Unfortunately, because of those hidden complexities, we often get this process wrong. So today we're going to introduce a new orthogonal approach. Instead of creating entirely new protocols from scratch, we'll use small local rewrites to modify distributed protocols over and over again until we have one whose performance is comparable to a hand-optimized protocol. In other words, we want to create a query optimizer or a compiler for distributed protocols. And here's why that's a good idea. So first, notice that these green check marks have shifted from being over the protocols to being over the rewrites, these arrows. And that's because we no longer need to prove that the new protocol satisfies invariance. Instead, we just need to prove that the rewrites do not change semantics. And because our rewrites are small and local, our proofs are also small and local and much easier to get right. The other thing is that because our rewrites are general, we can now apply them to any distributed protocol, including those hand-optimized protocols from earlier. Okay, so here's what that's going to look like. We'll take in a protocol, we'll implement it by hand in our Dataflow DSL, which I don't have time to go into the syntax of, but you can imagine something similar to TensorFlow, MapReduce, or Apache Flink. Once we have that implementation, we'll apply rewrites, and I'll break that into three parts: where to rewrite, which rewrites to apply, and how to correctly rewrite. And today we'll just focus on how to correctly rewrite, because I think correctness is both the most important thing in distributed systems or protocols, but also the hardest part, right? So we want to get that right. Okay, so let's say we're given a protocol and it's made up of a lot of components, right? Or nodes. This is how we're going to visualize it. So this box represents a node. These circles are operators within the node, which communicate with each other through data flow, these arrows, and can receive input messages and send output messages through these dashed arrows. Okay. Okay, so we have a protocol with a lot of components like this. How should we rewrite it? Well, first we should agree on why we're rewriting the protocol, right? What's our goal? So you could be rewriting protocols for throughput, latency, or fault tolerance, but for this talk, we'll just focus on throughput, okay? So generically, if you had a protocol and you wanted higher throughput, how would you get higher throughput? Well, if you knew that the protocol was bottlenecked on a single node, then if you could just reduce the load on that node, then you should be able to get higher throughput, right? So there's two generic ways of going about this. The first is decoupling, right, which is just shifting some logic, some operators to a different machine and changing the data flow between them into message passing. And the second is partitioning, which means creating a bunch of replicas that execute the same logic, the same operators, but then having the sender to those replicas decide which one to send data to, right? So intuitively, decoupling reduces load because you're executing fewer lines of code, and partitioning reduces load because each machine is processing less data. Okay. All right, so let's take a look at a real-world example. Let's try to rewrite the Paxos leader, right? And again, you don't have to know what the Paxos leader does, but essentially it receives messages from the client, sequences them, and then broadcasts them to some backups, right? Now, if you actually know what the Paxos leader does, obviously it does many more things than this, but for this example, let's pretend this is all the leader does. And we know we can't optimize sequencing away, but what we can do is reduce the load on the leader by decoupling, right? So we move the broadcast to a separate node. Whenever you want to broadcast a message, the sequencer just sends a message to the broadcaster, and then the broadcaster broadcasts, right? Now that we've decoupled the broadcaster, we can also trivially partition it, right? So we can just have a fleet of broadcasters, and the sequencer just round robins which message to send, right? Okay, so this is a pretty simple, trivial example of decoupling and partitioning, but we're going to take a look at more complex ones in the rest of this talk. Okay. By the way, we won't have time to talk about partitioning, so we'll just focus on decoupling for the rest of this talk. Now let's take a quick sneak preview of our performance, right? So across voting, 2PC, Paxos, and PBFT, after we've applied many rounds of decoupling and partitioning, you can see that we get anywhere from 2 times to 5 times increase in throughput, right? So that's pretty good. But what I want to focus on right now is what we didn't have to do to get these numbers. Okay, so we didn't have to prove that the rewritten protocol was correct. Right? We also didn't have to write down any invariants or specifications for the protocols. Right? There's no model checking or theorem proving involved. All we actually had to do was apply the rewrites wherever the preconditions were met. And this actually fits quite nicely into our architecture slide from earlier. How do we correctly rewrite? Well, we just apply rewrites wherever preconditions are met. Right, so clearly, a lot is riding on these preconditions. And we'll spend the rest of this talk going over exactly how we came up with these preconditions. But first, we have to talk about correctness, right? What does it even mean to be correct if we don't have specs or invariants, right? And then once we have a definition, we can talk about, well, what's an example where decoupling goes wrong, right? How does it break that definition? And then once we have an intuition of how decoupling can go wrong, we can use that to help us come up with preconditions where it is correct to decouple. And finally, we'll go back to the numbers I just showed you. Okay, so let's start with correctness. Traditionally, I would begin this section by coming up with a list of invariants and then proving that our new protocol satisfies those invariants. But so that would be a feasible approach if you just had one protocol and a bunch of PhD students lying around. But that's not the case, right? We're trying to do something very ambitious here, which is to create an optimizer that can rewrite any distributed protocol. So we're going to have to strive for a humbler proof goal. Okay, instead of proving that the new protocols satisfy the same invariants, we'll just prove protocol equivalence, right? That the new and the old protocols behave equivalently. And that'll imply that the invariants are preserved. Actually, well, it'll turn out by the end of the section that we don't actually need to prove protocol equivalence. We just need to prove observable equivalence, which is to any observer, it appears as if the new protocol is equivalent to the original. And that will also imply invariant preservation. Okay, so let's start. Let's start with our old goal, right? We want to prove if we're given an original protocol and it satisfies some invariants, then we want to prove that after we rewrite it into a new protocol, it also satisfies those invariants. Unfortunately, this is pretty hard to automate, right? So here's a paper from OSDI 2021 where they try to automatically find invariants across a bunch of different distributed protocols. And you can see that for Paxos, they timed out after a week, right? So they just could not do it automatically. In general, it's pretty hard to automatically find invariants for distributed protocols, right? So we're going to avoid this approach altogether. And let's go back to what we're trying to do here. We're trying to show that our new protocol preserves the same invariants as the original. But we already know that the original protocol preserves those invariants, right? So we don't actually need to prove that the new protocol satisfies those invariants. We just need to show that the new protocol is equivalent to the original. In other words, we just want to show that the rewrites do not change the program semantics, right? And this is something that query optimizers and compilers do all the time. So this means that we're on the right track, right? Now, what do I mean by protocol equivalence? Well, a little more formally, I'm trying to say that given the same inputs, with the same ordering, the new protocol and the old protocol must have the same set of possible runs. where each run is defined by the outputs and their order. Okay. Now, notice how I'm saying runs instead of outputs, right? And that's because many of these protocols are non-deterministic. Okay. And that means the random shuffling of the network may cause the protocol to produce different outputs given the same inputs. So we're comparing the possible runs as opposed to outputs between the protocols. But the problem with this is that it imposes a challenge in our proof, right? Because now we have to reason about a potentially infinite space of possible executions. And this is actually where a lot of model checkers get stuck, right? Because they're iterating through all these possibilities. So it'd be nice if we didn't have to do that, right? If we could just, look past this non-determinism. So the first thing is that I will claim non-determinism comes from the network. All non-determinism comes from the network. Okay, so let's say we have two nodes, blue and yellow, and they're trying to send a message to this white node on the right. Even if we can control exactly when the blue and yellow nodes send messages, we have no guarantee on when the white node receives those messages or in what order, right? And that's because of network non-determinism, right? Now, I know that you can have other sources of non-determinism, like depending on the local clock or random number generators. But for now, let's assume that it all comes from the network, okay? Then, if I can just zoom in on the perspective of a single node, we should be able to avoid reasoning about non-determinism. So here's what I mean. If somebody sends this node a message, we just care about when it arrived. We don't care about when it was sent. If this node sends somebody else a message, we just care about when it was sent, not when it arrived. In general, we're avoiding reasoning about how long messages sit on the network because that's the non-determinism, right? And now all we have to do is prove a node equivalence, which now compares the same outputs given the same inputs, not possible runs. And that's because each node individually is now deterministic. Right? The protocol as a whole might still be non-deterministic because of the networking, but each node does the same thing when you give it the same inputs. And that makes the proof much easier to prove. And as it turns out, this fits perfectly with decoupling and partitioning because both rewrites take a single original node and rewrite that into multiple new nodes, right? So we just need to prove that the new nodes together emulate the behavior of the original. Okay, so let's do a quick sanity check. Can we, just sketch a proof of how decoupling preserves node equivalence? Well, let's see, okay? So here's our definition of node equivalence again. If the original node receives a message at time 0, it will process that message and output that message at time 0, let's say. Okay, in our new nodes, if it receives a message at time 0, the first node will finish processing and then send that message to the second node. Right? Let's say the network delayed it by 5 time units. Then the second node will receive that by time 5 and then output it at time 5. So we have a problem here, right? Like 5 is not equal to 0. So decoupling did not preserve node equivalence. Okay, but what if I say that's okay, right? In fact, given any generic node that receives and sends messages, it's okay to delay incoming messages and it's okay to delay outgoing messages, right? That's because no observer will be able to tell, right? An observer is just anybody who sits outside the protocol and they can only communicate with the protocol through messages, and therefore they can't tell when their message arrives at the protocol or when the protocol replied, right? These two runs will appear identical to an observer, right? So in this case, the observer can send a message at some time 0, and then receive an output at time 5. And it won't know if it was the first case where we artificially delayed input and output messages, or the second case, right, where the network just non-deterministically delayed those messages. Okay, so that's, yeah. So instead of proving node equivalence, what we actually want to prove is this observable node equivalence, right? In the eyes of an observer, it can't tell an execution of the new protocol from the original, right? A little looser. Okay, here's kind of what that looks like formally, right? So it's a bit much, so let me walk through it. If the new nodes receive a message at time t in and output it at time t out, then we have to claim that there's some actual time of processing, right? Some t between the t in and t out. And then we have to find a run of the original node such that it could have received a message at that time t and output a message at that time t. Okay? Here's a visual representation of what I mean. Let's say the observer sends the new nodes a message and it arrives at t in, but we actually process it at t, right? Because we artificially delayed it. Then, as long as then actually we know there's an original run where the network also delayed that message by the same amount and then just processed it at time t, right? And then similarly, if we delay the output, such as only output at t out, then we can say in the original execution the network could have also delayed that output message by the same amount of time, right? Okay, so this will turn out to be the proof goal for the rest of this talk, right? We will prove observable node equivalence. All right, let's quickly summarize this section. We started out trying to prove invariant preservation. That wasn't feasible to do automatically, so we instead tried to do protocol equivalence. And then we realized that because everything is from the perspective of an observer, we can actually just prove observable equivalence, right? And the interesting thing, I think, is that the network non-determinism both helped and hurt us, right? So because it hurt us because it made us reason about the set of possible runs, right? Instead of just outputs of a protocol. But it helped us because now we can artificially delay input and output messages and just kind of blame it on the network, right? Okay. So that's it for correctness. We want to prove observable equivalence. Now let's take a look at how decoupling might break that observable equivalence. But we'll start with a running example, a messaging app that broadcasts all messages to all current members. So it can receive messages as input. It'll filter them based on maybe like swear words or something, and it'll tell whoever sent the message, hey, the message passed the filter. It'll also maintain a list of members, and then when it receives a message, it'll just broadcast that message to all current members. Okay? Now let's say this filtering was really expensive because we were doing it in an LLM or something, right? So we want to move that to a different machine. So we'll just decouple that and the broadcast, right? Filtering on node 1, broadcasting on node 2. Seems okay, right? Well, maybe not, right? So our adversarial observer here will actually show us how this is broken. And its job is to show that there is a run possible on the new nodes that was not possible on the original. Okay, here's how it's going to go about it. So first, they'll add our best friend as a member. Then it'll send a message into the system saying, you're my number one best friend. Okay. It'll wait for that message to pass the filter, which implies that the message was also sent to our best friend, right? Because both operations used to be on one machine, so they must have executed atomically. And now it'll add friend 2, right? Who is not supposed to receive this message because otherwise that would be a little awkward, right? Okay, let's see how that works out. We have our original node on the top left, new nodes on the bottom left. Okay, and then some space-time diagrams on the right-hand side. So let's say we sent this our best friend, right? And then we added the you're my number one message, waited for it to pass the filter, and then added our second friend, right? So in the original run, or in the run over the original node, we know that because the message already passed the filter, it must have been broadcast to our best friend. So eventually our best friend will receive that message and our new friend will never receive that message, right? It's impossible. But in the new run, if node 1 only then sends the message to node 2 after friend number 2 has been added, then the message might be broadcast to both our best friend and this other random friend, right? Pretty awkward. So what went wrong here, right? But what went wrong is that decoupling broke atomicity, right? So these two operators, which by virtue of being originally on one machine, would have executed atomically at a single point in time, now cannot possibly execute atomically, right? They're on two different machines executing at different times. So I guess we're done here, right? Like there's decoupling will always break atomicity, so there's nothing we can do. But well, no, okay. So remember, we're trying to prove observable equivalence, right? We just need to show we just need to decouple wherever the observer can't detect a break in atomicity. So let's try to figure out how the observer, figured out that we broke atomicity in the first place. So I claim that there's three reasons. The first is that node 1 told the observer when it finished executing. And then the observer was able to send a message to node 2. And then node 2 told the observer when it processed that original first message, right? And it indicated that it processed it late. Okay, and this is kind of what our counterexample is doing, right? Because we send a message to node 1, you're my number 1 best friend, waited for it to pass the filter, added our random friend, and then by circumstance, if our random friend receives this message, we know something went wrong. Another way of thinking about it is to imagine our adversarial observer as like a prosecutor. Okay, so its job is to build a case that shows something that must have executed atomically would no longer executed atomically, right? That our execution was non-linearizable because originally there was one moment in time in which it could have been processed, just the linearization point. And now there's two different, intervals of time where it could have been processed and they do not intersect, right? And here's how it did it. So first it sent a message to node 1. I don't list this as one of the ways the observer built its case because almost all useful nodes receive messages. But then node 1 output a message to the observer. So it told the observer like, hey, I got this message and I processed it. So that lets the observer first build a time interval, right? Somewhere between the send and the receipt of this message was when it was processed. Okay, somewhere in there. Then the observer sent the message to node 2 and got an output from node 2, which indicated when node 2 processed the first message. Right, so that, again, lets it build another interval of like, well, node 2 must have processed this message somewhere in here. And you can see here that those two intervals do not overlap. Right, so now the observer has a proof. Hey, you said there was going to be one linearization point, one point in which it was processed. I'm now showing that there must be at least 2 points, right? And they're in different intervals. Okay, so this is exactly what the observer did to show that the decoupling was incorrect. Now let's use that as intuition to help us find conditions where decoupling is correct. So we're going to take the three things that the observers exploited about our running example and then flip them on its head, right? Look at versions of our running example where one of those three properties are not true. And then we'll try to see if that helps us prove or helps us create a precondition. Okay. So as it turns out, it does. Here's the preconditions that we create. We're going to start with removing this property number 2. Okay, we don't actually look at number 1 because it doesn't turn out to be that helpful for our rewrites, but it is also a valid precondition. Okay, so what if nobody can talk to node 2? Here's what that looks like, right? I just take the input channel node 2, boom, make it disappear. I removed the names of the input and output messages, the channels, and the names of the operators because we want to make this a little generic, right? Given any protocol, any node in any protocol, and if it looks like this, can we decouple it? And by the way, you don't need to just have one operator in node 1, node 2. There can be many. Okay. All right. So let's try to prove observable equivalence, right? Does this do the same thing before and after the rewrites? Okay, so we have the new nodes on top, the original node on the bottom. Let's start just by analyzing the left operator, right? The first operator. So if the new nodes receive a message at time t on the new operator, it must also be able to receive that same message at time t in the original node, right? And if the new operator outputs, completes processing, outputs a message at time t, the original node could have done that too. So not a problem there. What about the second operator, right? The one on the right. We have a slight problem here, right? Because now the second operator might receive things late, right? Because the first operator received something and then sent it to the second operator as a message, where this channel was not a message channel before, right? So now it, is processing something at T out. We actually said that this delaying was fine. Right? Remember when we talked about observable equivalence, we said, we can delay outgoing messages. That's okay. So the actual question we want to ask is, sure, it's delaying output messages late. Are they even the same messages, right? Can you process the same messages later and get the same outputs? Hard to say. Right, and here's where the precondition was useful, where we removed that input channel to node 2. right? Because if you think about it, uh, in our running example, the observer sent a message to node 2 to kind of like interfere with its processing, right? It kind of asked node 2 like, hey, where are you right now? Did you get the first message? And now the observer is not allowed to do that, right? So that means if node 1 just recorded the message, the order in which it processed every single message, then node 2 could just process the messages in the same order, right? There's nothing from outside that can be interjected. So it's really just processing everything in the same order, just a little later, right? Just shifted down. And this is enough to prove that it will output the same messages if node 2 is non-deterministic, right? If the input ordering is the only thing that node 2's outputs depend on. And this kind of recalls the non-determinism from the network argument that I made earlier, right? If non-determinism came from anywhere else, like a random number generator or local clock timeout, this would not work. But if the output was solely dependent on input ordering, then yes, we will get the same outputs. Okay, and that's it. That's our proof sketch, right? So we call this state machine decoupling because node 2 behaves like a state machine. And the preconditions are node 2 has no inputs and it behaves like a state machine, right? Okay, so here's what that looks like in the paper. It's a little complex because we have to define what a state machine is and then use that to create an inductive proof. But yeah, so that's one precondition. Okay, let's see if we can do more, right? What about the third precondition, right? What if node 2 doesn't reveal when the first message was processed? Okay, so we'll change our running example a little bit. Everything still looks the same, but in the wording, I will say, instead of broadcasting all messages to all current members, it broadcasts all messages to all current and future members. Okay, so if you send in a message and then add a member, that member will eventually receive that message. Doesn't matter the order they were added, right? Okay, in that case, the observer doesn't have a gotcha moment, right? Where it says node 2, you send a message to somebody you shouldn't have, right? Because everyone eventually receives everything, right? In which case, node 2 is safe. We call this monotonicity, right? Because node 2 behaves like a monotonic function, a mathematically monotonic function. And as a result, it's order insensitive, right? As long as it receives the same members and messages eventually, we'll send everyone the same messages, okay? Now, I won't go into the proof again because we don't really have time, but this is the another precondition for decoupling called monotonic decoupling. And this is what it looks like in the paper. It's a little shorter because we lean heavily on the Kahn theorem for proof. Okay, lastly, here's another example of when node 2's outputs don't reveal when the input was processed. And simply put, the messages just do not touch each other, right? So node 2, it processes each message and translates it into Spanish, and it processes each member and tells you if they can speak Spanish. But the messages and members don't interact, right? So in that case, you can't use, the output of node 2 processing a message on node 2 to tell you if a member existed, right? So node 2 is functional. It has no side effects when it processes anything and no memory, right? So you can't use one output to detect if something else has been processed. We call this functional decoupling. And if you remember our example from broadcasting the Paxos leader, that was functional decoupling, right? Okay, here's what that looks like in the paper. And then we're done. That's it for this section. So we've just come up with 3 preconditions for decoupling. And we used the intuition for when decoupling is incorrect to come up with these preconditions. We have a bunch more decoupling and partitioning techniques in the paper, but I won't have time to go through that now, okay? So please just read our paper. All right, let's go into some numbers finally, okay? All right, so let's recall our architecture. We started with a protocol, implemented in our DSL, applied some rewrites. We didn't actually, create something that can be executed at the end, right? And in general, it's actually pretty hard to run data flow programs efficiently. So luckily, I didn't have to solve this problem on my own because I'm a part of this group called the Hydro project at Berkeley. So our DSL is HydroFlow, the language of Hydro, which is compiled down to this intermediate representation. And then there's this other thing called Hydro Runtime, which determines the scheduling of those data flow, and then compiles everything into Rust binaries. right? And then these can be deployed onto machines in the cloud. Here's all the people that I had the good luck of working with. And obviously my advisor Joe on the top left. Okay, so now here's our evaluation. We implemented 2PC voting, Paxos, and PBFT and HydroFlow. I put an asterisk on PBFT because we just implemented the critical path, right? But we know that we can optimize the whole thing. We just haven't implemented it yet. We ran this on Google Cloud on machines with 4 CPUs each. And then we did a greedy manual optimization. Okay, so we looked at each protocol, found the bottleneck, decoupled it, and then tried to find the next bottleneck. Once we were done with that, for every node that was partitionable, we would try to partition it 1, 3, or 5 ways. In case you're curious, here's all the rewrites that we did to these protocols. You can see that there's a trend towards more and more sophisticated preconditions, the more complex a protocol is. Okay, so here's our results. The graphs look a little different because they're now throughput latency graphs, but the earlier throughput graphs were derived from these. Now, the way you read these graphs is throughput is horizontal, latency is vertical, and the maximum throughput of a protocol is just roughly where the latency spikes up. So, for example, like voting, latency spikes up around where throughput is 100, so we say that its maximum throughput is 100K, right? 100,000 commands per second. Yeah, so these numbers are pretty comparable with implementing these protocols in your favorite programming language, right? So HydroFlow is doing pretty well. All right, now let's see what decoupling brings us. Okay, so across these protocols, anywhere from maybe 50% boosts to maybe like 250% boost, right? Not bad. Okay. Now let's take a look at partitioning. So you can see here in the green and the red, quite a lot of improvement, right? Now, one thing to notice is that in a lot of these protocols, the 3 partition in the green and the 5 partition in the red don't have that much of a difference. And we suspect that's because in these protocols, by the time that we're partitioning these nodes from 3 to 5 partitions, the bottleneck is no longer there, right? So it doesn't really help to just have more nodes. Now, lastly, let's look at latency, right? So theoretically, every time we're adding more rewrites, we should be increasing latency because decoupling increases message hops, and partitioning means that you're waiting on the slowest partition, right? Okay, so you can see across these protocols that the more sophisticated we rewrite, or the more layers of rewrites we add to these protocols, the higher their latency gets, right? At the throughput 0 case. But as you add more clients, the throughput very quickly becomes a problem, right? The latency is no longer the issue. Okay. All right, so that's it for these 2 talks, or these 2 papers. What's next? Well, the first thing is we would love to automate this process, right? We just talked about how we manually apply these optimizations, even though we did it in a systematic way. But in order to automatically do these optimizations, we would have to analyze protocols for preconditions, apply the rewrites automatically, and then automatically infer where the bottleneck shifts without having to redeploy the system. Right? So that's what we're currently working on. If we have that done, we should be able to scale anything, right? Not just distributed protocols. You should just be able to take a single node program implemented in our Dataflow DSL, throw it in here, see if we can scale it up for you. The other thing is now we can try to automatically change our protocols based on the current workload, right? If we can come up with a clever way to migrate data so that it doesn't really impact performance, then we can just switch configurations. Another interesting thing is to further explore this idea of automatically correctly decoupling code, right? So partitioning is pretty well explored in database literature, but decoupling is pretty new, right? We haven't really had a way to automatically cut up your code before. So this could lead to some pretty cool results. And one of them is maybe we can do some hardware acceleration with some parts of our code, right? Or in this case, maybe we can move some parts of our code lower down into the kernel. Maybe that'll give us some better performance. Lastly, I have a question for the community as a whole. What other rewrites can we generalize? Because partitioning and decoupling are both pretty simple, right? It'd be really cool if we could figure out exactly how we went from Paxos to any of its variants and then generalize that, right? And say hey, we automatically create ePaxos and also ePBFT and E2PC and stuff like that, right? This will likely require a different proof framework because now we're reasoning about much larger rewrites that go across just rewrites or go beyond just rewrites on single nodes. Yeah, but if I had time to do another PhD, that's what I would do. All right, so in conclusion, we can automatically rewrite distributed protocols. It is possible. The proof of correctness depends on observable equivalence. Right? We just need to make sure that the observer believes that the new protocol is no different from the original. Naively, rewrites can break correctness, and we should use that as intuition to help us create preconditions for when rewrites are correct. Thank you.